and welcome to another demonstration, that is demonstration 3 of this course on digital image processing softwares. So, first what I am going to do, I will go back to our software which we have been using, that is the DIP one, and then we will see that different functions which earlier we left there, we will be using those one. Especially first about the filter exploration. We completed up to this part. When there is some noise, we can use certain functions and can get rid of those noise or stripes. Removing stripes in frequency domain you have also seen. So, now let us go for spatial filtering, which we have already discussed in theory, and in this one I will keep like this. Okay. So, now you are having input image here, what you are seeing, a filter which is a low pass filter. We later on we will be also choosing the high pass filter. So, in a inbuilt low pass filter, that means highlighting the regional features and de-emphasizing or suppressing local features. And when we apply this filter over this input image, and then for as you can see on the right side, that all kinds of calculation is going on. So, for pixel after pixel, as cursor is also moving, and what we are seeing, and that calculation is done. So, I stop, say for example, at this pixel which is marked here as blue, and how this calculation is being done, because it is a 3 by 3 filter. So, around 66 pixel number 66 or the pixel which is having value 66 are all values around that pixel are considered in this domain, in this filtering. And what we are seeing, that everything is multiplied first by one value of 1, as in the this 2-dimensional matrix or in convolution filter is, and then for example the pixel 1 is 95, multiply by 1 will remain 95, and likewise all these filters, all these pixel values are first multiplied, there then sum is taken, that sum, the kernel sum is 9 of this, because all the values here are added. So, this is called kernel sum, and then it is divided 708 by 9, and we get a value 78, and this is what we are getting value 78 here for that pixel, which is now this is 78 where my cursor is. So, likewise when I do for all the pixels except pixels at the boundary or at the edge, at the same time you are also seeing the changes in the image is taking place in the bottom. So, if I want to this is these are the digital numbers which are displayed here, and the same numbers are displayed here as gray values too. And here this is the filtered image of this on the left side, and except for edge, when we have been discussing the theoretical part in spatial filtering, I said that if your filter is of 3 by 3, then one line on all sides, one pixel thick line on all sides will not be considered for any kind of filtering. So, this is what has happened, that only all these red pixels are now the modified pixels or filtered pixel. As you can see, original value was 80, now it is having 63, and here original value was 95, it is having 69. Now, because it is a low pass filter, and therefore the differences among pixels were in this area, originally they were large, that means they had local variations high. So those have been suppressed using this spatial filter, that is low pass filter, and now in the resultant image what you see, the variations in the pixel values have reduced, and that means that the local variations have been suppressed and regional variations will be highlighted or are highlighted here in this example. So what I will do, I will again press, I will restart again, and slowly we will go once again to see that when I run the filter, this is what I see, that now this this one, the pixel which is having value 80, that is calculated, but all these pixels in the surroundings have been taken into consideration, and their multiplication factor in this case is all is 1, that is taken. Then there is sum is taken, divided by 9, that is the kernel sum, and then you get a 63 value. So once I accept this one, then you see that the value is 63, and likewise all the pixels except at the border or on the edge, 1 pixel thick edge will not be considered, and you get, if I want to show you the pixel border, that is also there. So this is how the low pass filter works in the real image scenario as well. But what the best advantage by this software by Dr. Rathore, Chinmay Rathore, is that it simulates the things, it shows that what kind of calculation is going on if we talk about low pass filtering inside a conventional or a commercial digital image processing software like ADAS or any other NV or maybe other powerful softwares, ER Mapper or others, what kind of calculations are going on in the behind, and that too for a large image is all depicted here in a very simple way. So that is why I have been emphasizing that this software should be downloaded by those who are interested in digital image processing in this course, and should learn the fundamental basics and the mathematics which is going in the back. Now what I will do, I will start afresh, but now I will take, instead of low pass filter, now I will take high pass filter and see how things changes in high pass filter. First we will discuss this convolution matrix, and that is a kernel, and this is again 3 by 3. In this example we have taken, if we take 5 by 5, then 2 pixel thick line on the edges will not be considered in the filtering. If we take more, any odd number like 7 by 7, then 3 lines, and so on and so forth. So in this is the simplest example, it cannot be less than 3 by 3. So we are taking all values on the edges of this convolution matrix are -1, whereas the center pixel is 16. If you recall the theory part, when we have discussed in earlier lecture about the spatial filtering and especially high pass filter, the purpose of high pass filter is to emphasize the local variations present in the image and de-emphasize the regional variation, just reverse of low pass filter. So that is why there is a more weight for the center pixel value or center kernel, and rest is de-emphasizing, so that is why there are minus values. Now again the same way we will learn, we will run this thing step by step and see what changes it takes. So for the first pixel, that is 80, the pixel value which is having 80 is now calculation is being done. All this 55 multiplied by -1 becomes -55, and likewise all these values are done, and then what you get a value 98. So this value is has increased compared to what input value was 80, and likewise all these values are enhanced. So when we take this sum of after this multiplication, against for all pixels. In this example, for the 95 pixel, the pixel which is 95 value, and then divided by 8, then this we get 1, 2, 3, and likewise we start getting here. Because one value is positive, rest are negative, and therefore it is the division is 8, not 9. In the low pass filter, because all values were same, so division was 9, that's the kernel sum. And now this is what we are seeing in the high pass filter. So as you can see that when if you just compare this in grayscale also, that you don't see so many details in the pixels or differentiation in the adjacent pixels, but when it has been subjected to high pass filtering, now you are seeing lot of differentiation in the pixels in a local, that means adjacent pixel. That was the purpose of high pass filter, to highlight the local variations and suppress the regional variations. In case of low pass filter, the aim was just reverse, that to highlight the regional variations and suppress the local variations. So this is the demonstration of high pass filter. I will do it again just for completeness, and slowly I will run for the first pixel, and then second, and then next, and the condition is same, that one, because this is a 3 by 3 filter, so therefore 1 pixel thick border will be there all the time in the 3 by, because if I want to calculate for this pixel which is at the top left corner, then I don't have the pixels which are surrounding to this one, and therefore in this spatial filtering 1 pixel thick edge or border will not be considered in the filtering calculation. So this is how, in a very simple way, we can understand that how low pass and high pass filtering is done on a full size image. This is just a demonstration or simulation on a small. Now we take another one, which is ratio builder. As we discussed in earlier discussions, when we went to multispectral analysis, then band ratio, and also we discussed one more step forward in band ratioing, that is calculating NDVI, that is normalized difference vegetation index, to see the vegetation coverage, health of vegetation, and other things. So first we will go in this demonstration about the simple ratio, and as you know, the simple ratio is just A divided by B. So band A is here and band B is in the bottom. In the spatial filtering exercises, we were seeing the single band. Now here we are going in multispectral, so we are considering band, 2 bands here. One band, B may be infrared band, A may be a band from visible part of EM spectrum. So when we do this, then it is calculated, and we one by one again, and the entire thing has been done here, and what we see here, an divided A divided by B image has been created here. So if I want to see the value, like here I take this example here, what I see, the 91 divided by 63, that will come 1.44. But of course it has to be rescaled. So a scaling ratio to display values between 0 to 55, that is the to multiply, and then we get in form of pixel values. So we can also see the stretch mathematics here, or also show pixel borders, that is again on the board here the edge issue or the 1 pixel thick issue will definitely will not come. So, we again I will do it afresh, divide. Now image has been created and so stretch maths, and this is how the calculation is done. Let's see once again very carefully that pixel ratio for first pixel on the both bands, band 1, band A and B, and 91 and 63, that will turn out to be 1.444. So, minimum ratio is this one, maximum ratio is this one. This is stretch calculation for that pixel, cornered pixel, and in case of NDVI, in case of this normalization, because after all it has to be displayed, and we can in an image, if you recall, image in image the pixel which is the unit, the value or the attribute has to be a integer value. That means the pixel value in an image has to be a positive integer value, and after ratioing the value which we are getting is 1.44, which is not the integer value, it is the real or floating point value, and therefore it is in decimal. So, therefore, we have to multiply by 255 as shown here, and then we get a display value which is 180, which is being used here. So, likewise for each pixel this calculation is done and you get a ratio output of the image. So, I can do it again here and show this one, and then when I select this one, it is like. So, whenever if I want to do the analysis for similar analysis for this pixel, the same thing is here. The ratio value is 1.857, then minimum ratio is in the overall image is 0.44, maximum ratio in the overall image is 185. These two minimum and maximum are used as per this equation, very simple equation, that the pixel ratio minus minimum divided by here pixel maximum minus minimum, and then multiply by 255. Why 255? Because we are considering a 8-bit scenario. So, I hope this part should be very clear, that when we put or when we create an image ratio using two bands, in the background what kind of calculation goes against each pixel in the of image is clearly shown through this simulator, image processing simulator. So, it is in that way better to first to understand. See, the learning is step by step in this domain. First is theory part which we have studied or discussed about. Then through this simulator, now we are seeing what kind of calculation mathematics may be simple is going on while calculating either filtering or in this case band ratioing. And once you have understood the theory part, the simulation part, now you can go for the real image band ratioing and using maybe commercial softwares. Now I take I take now NDVI here instead of a simple band ratio. NDVI is also a type of band ratio, but like in calculation it is that because we use a visible or a near infrared channel or infrared channel, therefore it is dedicated, this kind of calculation, band ratioing calculation is dedicated for vegetation. So, that is why it is, and it is normalized. So, it is normalized difference vegetation index, because difference is we use a visible channel also. So, if I put these two bands A and B to the NDVI, this is what the result I get, and I can also see how the calculation is. So, same way if I put my cursor here, this is the calculation, that the pixel ratio which is based on this simple formula is 87 here in the band A minus 52 in the band B divided by 87 plus 52, and that way I get the value 0.251799, and when I multiply by this value to normalize it, then I get a value 236, which is the value of this pixel in NDVI image. So, in that way, when I do it for the entire image, as it has already been done here, then I get the health of the vegetation information. So, in many ways it is just like a ratio, but that is a simple ratio, band ratio, but NDVI is little complex in that sense that it has to be one visible band and one has to be the infrared band, and then you do it like this. So, infrared minus visible, infrared plus visible, whatever you get, you rescale it and then you end up. Of course, the same pixel ratio here is 0.251, minimum value is minus 0.381, maximum value is 0.3. So, these values have also been used during the normalization, so that we get an integer value in our output image. The pixel value in an image has to be integer, and that's the one condition. Only in GIS a grid can have integer values as well as real values and can also have positive or negative values, but image pixel value will always be a positive integer value. That is why all these negative values, everything has been removed through this normalization, and you get output like this. Now we will see another simulation, that is the image differencing, means image arithmetic. You can add two images, you can divide two images, that is band ratioing, you can subtract image one band from another band. So, this is simple demonstration here, that we will subtract from image 1 and we will use this image 2, and when we do it, this is what we get. And then we can see in form of image or we can see in form of data. We can also swap these images, that image 2 will become image 1 and image 1 is 2. Now, when we subtract like here, then we get this thing, and in terms of pixel or in grayscale, this is what the result is. So, if we linear stretch on the image, this is what the result. If we go for pseudo stretch, and then there will be result again, and I choose say no stretch likewise. Sometimes in some analysis, simple image arithmetics has also to be applied, and therefore these tools are also supported in your digital image processing softwares. In filtering, what we have seen, low pass filter, high pass filter. Now we will also see edge enhancer, that enhancing the edges in the features, and this is of course a high pass filter, as this convolution matrix you can see here. So, if I load this this one and run this one and see that the values are same way are calculated, then it is the CP value is now this 99, and then plus filter sum. In this case, filter sum is 0, because here this is the these values are being used, and therefore I am getting value 99, and likewise all these values are there, and what end result is that things edges means the difference between pixel values. Suppose they were difference of two pixel values, one value was 75, another one was adjacent value was 77 of 2 adjacent pixels. After this edge enhancement filtering, high pass filtering, because it is a local enhancer filter. So, it will create more difference between adjacent pixels. So, example 75, 77, the difference may be now 72 and 79 or maybe 80, and this is what you are seeing, that in this input image the values are, this is the edge which has been identified here or marked here, and if I want to enhance this edge as is done in this case, then the difference here, see the difference. Now earlier if I take this pixel, this was 99 and 69. Now this value, the 99 has gone to 129 and the 69 has gone to 39, and that means there is more difference between two adjacent pixel values, and that means the edges has increased or enhanced. That is why it is called edge enhancement filter. And so one can do that kind of analysis in real softwares, not in simulator. And earlier discussions I have shown you through images, when they were subjected to edge enhancers, we get a very good output for linear features extraction or identification of linear features. However, one important thing which I would like to bring here is that whenever one is going for, of course this is a simulator, so it is fine that we are having a convolution filter, that is high pass filter, and that is 3 by 3. But in real operations, when you go with the for the real image in powerful softwares, what do? You take rather than 3 by 3 convolution filter, you go for 5 by 5 or 7 by 7. In our discussion in theory part, what I have shown the example of 11 by 11, though it will take lot of time, but it will really highlight all the edges very successfully. So, in edge enhancement filters, a larger convolution matrix should be chosen, and then one get the one other thing is that if you recall the low pass and let me show you the low pass and high pass filters. And low pass filters here all are examples from 3 by 3 convolution matrix. So, low pass filter what you are seeing here are having all positive value, that is 1. In high pass filter, on the edges of this 3 by 3 convolution filter, you are having negative values, and in the center weight, because after all this is weighted average. So, center weight is having a positive value, that is 16, because in that way one can design 8 or put whatever is there, but to more the weight it will have, higher the enhancement it will do for high pass in this example. But when we if you see carefully in edge enhancement filters, though again it is a 3 by 3 convolution matrix, corner values have been kept 0, that means no change is required. However, north south and east west, here the filters will be reverse in that sense, that when I say north south, that means I am talking about these values, when I say east west, then I am talking about these weights in the filter. In the image it is when it is east west, in the image east west, north south. So, now here you see in the first row of this convolution matrix, you see the middle pixel, middle cell is having -1, same here in the first column middle cell is having -1, again in the bottom -1 and -1, and the center one is having positive value. So, you can also notice a clear cut difference between low pass filter, high pass convolution matrix and edge enhanced, though it is a high pass filter, but of a different design. Now, when you are using 3 by 3 convolution matrix, the options for designing either low pass or high pass filters, especially high pass filters, are very limited. You can realize by now that in 3 by 3 convolution matrix not much maneuverability is available. Whereas as you expand this, instead of 3 by 3, if you go for 5 by 5, then more options would be available, and you go higher and higher in the size of convolution matrix, more options would also be available. So, in that way we can see lot of changes there in our image, and the purpose here of showing, again I am repeating, that to demonstrate what kind of calculation goes on when we put images either to filtering techniques, spatial filtering techniques, or to band ratioing or NDVI or edge enhancement. All those things are there. Now I will very briefly I will also touch in this discussion or demonstration about a software which is commercial software. But let me make it very clear here. And the purpose of using this commercial software is just to demonstrate what we have been discussing in the normal lectures or theory lectures, let me say like this. The purpose here is not to promote any software, especially the commercial one. There is no intention at all to promote any softwares, but in order to demonstrate what we, or in order to further understand what we have been discussing in theory classes, then we need to use instead of a simulator, we need to use a really a powerful software to show all those things. Now what I will do here, first I will take an image which earlier also we have taken that image, and then see that what happens to this image. I also showed this image through a different commercial software, that was ArcGIS. Now here, when first time you display this image, as also happened in case of ArcGIS, that it is in a different scheme. So I will change this scheme, and now I am getting in real RGB, means it is a false color composite. 3 channels are there of a spot satellite, which was a friend satellite of Moscow city, which you are seeing, and 3 bands, and this is not enhanced at all. No image processing has been performed except a false color composite has been created on this image. This is example image of ArcView software. So it is a very sort of a standard image. If you want to do it you want to have a real experience, then you must download an image which is available through various resources, and then you start doing this kind of processing as well. Now there are a lot of enhancement which I can perform here, and some are some are there like if I go for this adjust radiometry, already the system has done on the image using different. So if I say this is basically the input image, in a very brief it is showing, and also when I put my cursor it is showing that this is the equal percentage. That means it is stretching the image to exclude the lower and upper 2.5%. So if you recall the histogram of or histogram of any image, so the tail part or both tails, 2.5% of the tails have been excluded in this enhancement, and this is what the result is you are seeing. And this is all, these are all prepared LUT based on our input. If I accept this one, then I get the display, otherwise I get. And next one is the left right percentage. Again what it says that it stretches the images to exclude the lower 2.5 and upper 1.0. In this one it was all along on both ends, both tails 2.5 were excluded. here 2.5 and 1%, and if it is here, this is standard deviation, that is stretching image enhancement based on statistical technique, standard deviation. So 2 plus and minus 2 standard deviation. So those have been those have been used here. Like here, the stretches the image evenly between plus and minus 2 standard deviation around the mean, and the output which you are seeing here. If I go for minimum maximum, basically we are going for a minimum maximum, that means everything is being kept, and in this example we are basically reaching to the original image. So there is hardly any difference between the no stretch and minimum maximum. But if I go for this is simple linear, I can make lot of changes. This is Gaussian stretch, and this is histogram equalization. Recall our discussion when we discuss histogram equalization, which creates the maximum contrast in the image, and it is also demonstrated here. This is creating a maximum contrast because wherever the high frequency pixels were there, they have been redistributed, and wherever the low frequencies were there, they have been put other place. If you recall the histogram and the display, then the entire dynamic range is whatever is available has been occupied. This is 3 band scenario, so there will be 3 histograms for each band, and then it has been done. So if I accept this one, this is what I get. Again, if I go back here, this is gamma filtering or gamma stretches, which applies to the image with a value of 2.2, and though manually also you can adjust, but the software, whenever you choose an image or display an image in this window, immediately it will calculate lot of options for you, and without going for that one. And this is slicing or density slicing, which we have not discussed, so I will not touch. And this is invert, that inverts the value of image and can be used to correct a negative image, and that way it is there. So likewise you can very quickly, because these are of course commercial softwares and they have been made very user friendly. So all kinds of options very quickly you can perform these kind of adjustments. Similarly for filtering also, as you can see, a special filter which we have discussed, no filtering for the input image. So let me bring the original image here, and or rather little enhanced image like this one, and then I choose, this is my input image, and these are the filters. Standard filters are there, applies a standard edge enhancing filter to the image, and which you see here. You can have a other find edges. So it has now applied a very heavy filter, and only edges have been highlighted. Then smoothing, that is the low pass filter. So it is highlighting the regional things, as you can realize. So when you see this one and this one, is completely changed, though input image is the same. And of course then you are also having directional filtering, that only horizontal detects horizontal edges, and here of course vertical edges. So you are having low pass filter, this one, you are having high pass filters, this one, you are having high pass edge enhancers, this one, and then you are having directional filters, which are also in some way high pass filter for horizontal thing, and then you are having vertical things. So all these things are being done very quickly without you knowing that what kind of mathematics or calculations is going on. And that is why I have been emphasizing that for better learning and understanding of any image, one should definitely go for step by step, first understanding the theory part, then through this simulation, and finally through such a very user friendly softwares, and these are very well designed, very well coded, and that is why things are very quickly can be done here. And when we go for this one, there are all these options are also becomes available for against each options which are there. Again I will repeat and then I will close this discussion, that the purpose of showing through this commercial software is not to show the capabilities of this software, but to show how image processing can be done very easily once you understand the background and theory part. So this brings to the end of this discussion. Thank you very much.